So this lecture is about multiplying infinite series together, and this is something you've probably not seen in your calculus courses yet because it is considered to be old-fashioned, but quite frankly it is very powerful, and so let us proceed with it. Let's motivate this. What we're going to do, let's look at two partial sums. The partial sum of a sequence an, which I'm going to denote capital A sub n is a0 plus a1 plus etc. through little an, and then a sequence capital Bn, or a partial sum capital Bn, which is b sub 0 up sum through up little b sub n. And so when we multiply capital AN times capital BN, we can first take AN times the expanded BN, okay. Then we distribute that, and then each term I will expand my partial sum AN and distribute the particular small b's across that, so we have it out in this way. Then I can take that and I can regroup it in the following way, so that I have my first line a sub 0 times b sub 0, my second line a sub 0 times b1 plus a1 times b0. The third line, which has a typo in it, I have a0 times b2, a1 times b1, and this should be an a2 times b0, and I continue in this way till I get to the longest one. It's a0 bn, a1 bn minus 1, etc. And then we start removing a term of time at a time till I get to the bottom one. It's an times bn. Okay, so each of these rows across, the sum of the subscripts is the same. The top row, the sum of the subscripts is 0. The second one, the sum of the subscripts is 1. The third, the sum of the subscripts is 2. That's why I caught my typo there, and so forth. So we have all of the possible ways that we can multiply together my an times bn terms, and then they're connected together with a plus sign, okay, which is exactly what was happening on the previous page. Okay, so given that, let's define some stuff, and so maybe you'll see where this comes from. Given finite sequences, or excuse me, infinite sequences, an and bn, we will create a new sequence, cn, as follows. Each entry into cn will be the sum of k equals 0 to n of ak times bn minus k. So each of my cn's is going to be like one of the rows on the previous page. So this is C0, this is C1, C2, this long one is Cn, okay. Except if it went out to infinity. These were just finite sums, and so we're only legit as my Cn up until that point. Okay. Now, we say that Cn is a convolution. This new sequence, Cn, is a convolution of the sequences an and bn, and that if we take the sum of the series n equal 0 to infinity of Cn, that is the Cauchy product of the two series n equals 0 to infinity of an and n equals 0 to infinity of bn. Okay, so we've defined the Cauchy product of two infinite series. All right. What I want to do now is to work out an example here. So let's look at the geometric series 1 plus x squared plus x cubed plus x to the fourth plus x to the fifth, etc. I might not want to take it out that long all the time, but let's just take a look at this. And now, okay, I have an infinite series. If I want to make an infinite series for 1 over 1 plus x, what I can do is just substitute in a negative x everywhere there is an x in this series. So I would go 1, okay, minus x, okay, plus negative x squared is just x squared, minus x cubed, because negative x cubed is minus x cubed, and then plus x to the fourth, and then again minus x to the fifth, right? Because odd powers will take -1 to -1, even powers will take -1 to 1. So I have these two infinite series here. I'm going to multiply them together as Cauchy products. On one side, 1 minus x times 1 over 1 minus x times 1 over 1 plus x. And then that's on the left-hand side. On the right-hand side, I'm going to multiply them together like a Cauchy product. Okay, I'll go 1 times 1, okay, and then I would go 1 times negative x plus x times 1, okay, for the second. Then I would go, okay, 1 times x squared minus, okay, actually plus, excuse me, let's do x times negative x, then plus x squared times 1, and then plus, okay, 1 times negative x cubed plus x times x squared plus x squared times negative x plus x cubed times 1. And I could go on a few more terms. I'm just going to stop it there for the sake of time. But if I do my math on this, I'll get the top row is 1. Okay. Then I'd have minus x plus x. That's 0. I'll leave that out. And then I'll do x squared minus x squared plus x squared. That is plus x squared. And then I have, okay, minus x cubed plus x cubed minus x cubed plus x cubed. So that's 0. Maybe do it one more time just to show the pattern. I would go x fourth times, 1 times x to the fourth. Okay, that's looks like the dog's dinner. Plus x times negative x cubed plus x squared times x squared, and then plus, let's see, x to the fourth times 1. And what we see here, if this is done correctly, that'll give me x to the fourth. And so what we see here, the number, the rows that have an even number of terms, they'll cancel out. The ones where they have an odd number of terms will have 1 left over. And so this will go 1 plus x squared plus x to the fourth, etc. If we look back at the left-hand side, that 1 minus x times 1 over 1 plus x is 1 over 1 minus x squared. And to get it as an infinite series, I just replace each of the x's here with an x squared, which will give me 1 plus x squared plus x to the fourth plus x to the sixth, etc., exactly like what the Cauchy product gave me. So this will bring us to Mertons Theorem, and about when can we multiply together infinite series and get what we expect to get. And so suppose that the sum n equals 0 to infinity of a n converges absolutely to a number a, and that the sum of n equals 0 to infinity of bn converges to b. Doesn't necessarily have to converge absolutely. If the sum of n equals 0 to infinity of Cn is the Cauchy product of the series An and the series Bn, then that Cauchy product will converge to A times B. The proof of this is in the book, and to say that it is quite involved somewhat beggars the language here. I urge you to just look at it, trace your fingers through it, and thank your lucky stars that I'm not dragging you through it.